Hello, welcome to our last little video in this geometry unit before we move on to graph theory. This geometry unit, we're actually looking at some different concepts from something called topology, which I'll talk about in a minute. And the funny thing is, I say it's the last in the geometry unit, but we're talking a little bit about topology, and yet the next unit, at least for this course, is going to be on graph theory, which is also an area of topology. But anyhow, as the title indicates, we're going to be talking about something called a Mobius strip, something called a Klein bottle, and maps. And that is maps like you would think of them, like map of the US or something. All right, so what is topology? Topology is also nicknamed rubber sheet geometry because topologists like to think about, what if we imagined surfaces or objects to be made of some kind of a pliable rubber, and the only rule is we're not allowed to create new holes or cover up existing holes. Like whatever holes exist have to continue existing. But what are the properties and what can happen and what kinds of shapes are similar if as we stretch or bend or twist this rubbery material, with keeping that one rule about holes intact. So they like to see what properties are going to remain the same as you bend, twist, or stretch the rubbery, rubbery surface. So it's like a thought process. So the concepts were around for a while, but the name topology was used by Solomon Lefschetz. We're going to talk a little bit more about him down the road, but for now, just know that he coined the term topology in a paper in 1930. And then the joke is that topologists don't know the difference between a donut and a coffee cup, because with them thinking about things with this, with this thought experiment about, well, what if things were made of rubber? To them, a donut and a coffee cup, since they have the same number of holes, donut having the hole, like a traditional torus type donut, the donut has the hole in the middle, coffee cup has the hole where the handle exists. We're just talking about like traditional basic shapes here. And you can take one, if it's made of Play-Doh or something, and stretch it into the shape of the other and keep that one hole in there. And it's not always just thinking about rubber, but also thinking about, like, if something is already twisted in odd ways, can we classify it, or can we untwist it without breaking something? What can we do as we try to alter the shape without altering the number of holes, or like in the case of knots, like how many, like where it's actually knotted versus where it's just like overlapping or something. And what I was just thinking about with knots, there's an area of topology called knot theory that's pretty cool. I'm not going to talk about it anymore after this, but the concepts they explore with trying to categorize knots and trying to untangle knots can help with things like understanding DNA and infectious diseases. When things are tangled, can we untangle them, biologically, or how can we prevent them from getting tangled when they're not supposed to be, that kind of thing. Okay, so back to thinking about things with holes in rubber. When they talk about the number of holes through an object, that is the genus of the object. So when we were just talking about the donut and the coffee cup, those only have one hole. Coffee cup with more than one hole might be a problem, because then your coffee wouldn't stay in the cup, maybe, depending on where the hole was. But so those are said to have a genus of one because they have one hole each. If you just take a typical rubber ball, we're not thinking on the molecular level or on the microscopic level. We're just thinking on, like, if we just look at a rubber ball generally, we don't see a hole in it. So that would be a genus of 0. No hole, 0, one hole, 1. You might think of all kinds of other examples for these different categories. When I think of genus 2, I usually think about going to a water park and going on one of those rafting rides, like with my husband, that has the double holes. I drew that. It looks kind of like a mask, but maybe Zorro's mask too. You can think of that as having a genus of 2. The people get to sit inside the raft there. Genus of 3 if it has 3 holes, and so on. So drawing the donut earlier in the coffee cup. You know, your donut or your torus has the one hole. And then when you talk about your coffee cup, again, the handle is the one hole. So there's some really cool videos. If you go on YouTube, you just search for topological donut. And there's some cool videos that show the morphing process for this thinking about a donut and a coffee cup being the same. So that's something to kind of explore. All right. If you like to read about breakthroughs, a gentleman named Gregory Perlman, he's still alive, mathematician. He won the Fields Medal, which is kind of like the math version of a Nobel Prize. He did work in topology. Specifically, he solved something called the Poincare conjecture. If you'd like to read more about him, that link there tells more about his story. He is somebody on your mathematician list, so I do encourage you to go to that link and learn more about him. All right, another person that comes up in topology, Mobius. You guys might have already seen that I have a Mobius strip project for you to work on. You are creating your own Mobius strip, and you are going to do some experiments on it, and then write about like what your predictions are, and then write about your conclusions once you conduct the experiment, and then turn that in on Canvas. But that strip is studied by topologists, and it was extensively studied by the pioneer of topology, August Ferdinand Mobius. He was a German astronomer and mathematician who studied under Gauss and eventually became the director of the University of Leipzig's observatory. He also played a part in the systematic development of projective geometry. So with that little project, I'm having you guys take a strip of paper, and then I'm asking you to do a half a twist. So in other words, one end needs to be twisted so that front goes to back. You don't want to do a complete twist, you just want to do half a twist. And after you do your half twist, you're going to bring the flat ends together and tape them together so that you have kind of this little loop. And I'm going to leave it up to, I'm not going to talk about it in this video because I'm leaving it up to you to make some observations. Oops. And then you're going to share your observations and thoughts in the project. But the Mobius strip, nice little one-sided construct. A lot of cool stuff happens to it. Yeah, it's one-sided. Also, if you'd like to check out some art dealing with the Mobius strip, do a search for MC Escher's print with the ants crawling, and you'll see ants crawling on the infinite nature of a Mobius strip. And usually in class, we do a lot of this stuff in class, but you're having to do it online. Usually when I teach this lesson, I wear my earrings that are Mobius strips. They're little metal earrings, but they're in the shape of a Mobius strip. And I like to bring up that Mobius strips are also good for conveyor belts. Can you think why? If you'd like to think for a minute, maybe pause the video and answer, and then continue when you're ready with your answer. But if you think about a conveyor belt, like let's say it's on two wheels, usually you have your conveyor belt running around the wheels like this. But if it's in this little traditional pattern, it's going to be worn out on one side faster than the other, because there's one side that's constantly going around the wheels, and then the other side that's constantly got the goods or materials or whatever on it. So the wear and tear is not going to be even. But if you think about doing a Mobius strip kind of configuration, the Mobius strip has that little twist in it. In there. So it ends up wearing evenly on, well, technically a Mobius strip is one-sided, but that whole one side ends up wearing everything evenly. you don't have two sides where one side wears out faster than the other. So that's kind of a cool thought. Again, I'm no artist, so sorry I can't draw that better. Now, topologists aren't going to just stop with looking at one object. They like to stop and think, what would happen if we took two of these and glued them together? And that's exactly what they did with the Mobius strip. They thought, well, if we glued two of them together, what would that make? And that would make something called a Klein bottle. The problem is, though, Klein bottles only exist in four dimensions. So they can't actually create one in our world, but they can create what's called a 3D immersion. It's kind of like when you look at a 2D map of our 3D world. You're seeing it a little differently. Well, the Klein bottles, that if you go to that website, you'll see some glass-blown Klein bottles, both big and small. They look kind of like this. They have all kinds. If you have a little extra money and want to buy something quirky, they have like Klein bottle beer steins and all kinds of crazy stuff. But it kind of goes like this. And then you got this part that's on the inside here. And then it's kind of so the stem that kind of like loops into itself. But just check out that website, that kleinbottle.com. You can see some pretty cool pictures. Just remember that those are 3D immersions of a fourth dimensional object. But yeah, in your book too, you can go and see how it's basically two Mobius strips where you take the one edge of one and glue it to the one edge of the other, or tape it or whatever, fasten it together, and that's how you make a Klein bottle. A couple other different problems that topologists face. One is called the four-color problem. That's with coloring maps. They had thought that, like, if you draw a map on a plane, that like if you're making let's say you're making a big book of maps, like a geographer or something would do. They figured you could use a maximum of 4 colors and make sure to have no two adjacent regions with the same color. The problem was presented way back in 1852. Augustus de Morgan had a student that presented the problem. They weren't able to prove it until computers were able to help. In 1976, Kenneth Apple and Wolfgang Haken, with the help of 1,200 hours of computer time, were able to prove that on a plane, you only need 4 colors. So if you draw yourself a map, I'm just making something up here. You need at most 4 colors to color this in. So like if you color this part in green, you could color this part in blue. You could color this part in purple. And then you could use a 4th color, maybe red. As far as like shared borders, that's the only colors you would need. Then you could just do variations of that color elsewhere. And then no shared border would have the same color. This is kind of a simple version of the map that this works on, but so nobody who shares a border shares a color. Like that. That was a 4-color problem. But they looked into it too and realized that that's just for a plane. If you did a map on a Mobius strip, you would need at most 6 colors. Or if you did a map on a torus, you would need at most 7 colors. So just imagine like buying a donut. Maybe, let's say you have a donut that you bought at Krispy Kreme. I say Krispy Kreme, I love Krispy Kreme. Those donuts are very 3-dimensional. And let's say you have a map drawn on your donut. And you could still have stuff in there. So that's what they mean by, maps on the donuts. So a map on there requires at most 7 colors, so no more than 7 colors. Or if you decided to draw one on your Mobius strip, let's see here. This pad sometimes drives me crazy when I'm trying to draw on it. I'm not trying to draw. Alright, so let's say this is your Mobius strip. And then you have your little twist in there. So you have your little twist, but then let's say you draw a map on there. Then you need on that, you need at most 6 colors. So that's some of the fun they have. They like to look at other objects and think, well, what happens on those? Other topological type objects. They seem to love donuts. Jordan curves, last definition, topology, just throwing you some random stuff about topology. Last definition is a Jordan curve. Jordan curve is a simple closed curve, has an outside and inside. And there's a really simple mathematical way to decide whether a given point is inside or outside the curve. You can draw a line segment to a point that's definitely outside the curve. And if the line crosses the curve an odd number of times, then your point's on the inside. If the line crosses the curve an even number of times, then the point is on the outside. Really simplistic version of a Jordan curve would just be like a circular shape. Let's say you have a point on the inside and a point on the outside. You can draw a little segment between them, and you'll see that it crosses the curve only one time. That's an odd number. But you can make your Jordan curve a little more complicated. Like you could do it like this if you wanted. It's a simple closed curve. It's going to be closed. You're not going to leave any openings. And let's say you have a point right here, and you want to determine whether it's inside or outside. Then you could, like, let's just for the sake of playing with this, let's put a point over here. If you draw a segment from the point inside to the point outside, you'll see that it crosses 1, 2, 3 times. Crosses thrice. Yeah. That's another odd number. Alright, let's do one though where it's kind of this crazy loop type situation. This is how they have it in the book. They have one like this. Okay, this is Jordan curve. It's nice and closed. Let's say we put a point right here, and we're like, I'm not quite sure if that's on the inside or the outside. We'll put a point right here that's definitely on the outside, and we'll connect with a segment. Well, it crosses 1, 2, 3, 4 times. That's even, so that means that the point is on the outside. Then let's say we do a point that's here, and then do another one over here, connect with a segment that crosses 1, 2, 3, 4, 5 times. That's odd, so that's on the inside. And you can, I mean, you can tell from the center where the inside is, so I could kind of start coloring it with the orange just to show, hey, yeah, this is where the inside is of this Jordan curve, this simple closed curve. Topologists like to look at these and look at all kinds of characteristics with them. Versus the purple, we determined earlier that that was on the outside. Well, we were out here, along here, we're still on the outside of the curve as we spiral around. And you see that our purple dot was there where we spiraled, where the purple spiral is. All right, so there you go. There's some basics with topology, some basic definitions, some basic problems that topologists like to look at. Just want to give you an exposure to topology. You can take entire courses on this and do entire studies on topology. We're just going to we're going to look at our next unit on graph theory is an area of topology, and we're only going to touch the very basics, like the chapter 1 of topology. But if you're interested in this, there's definitely a lot of videos out there, a lot of cool stuff. So definitely check those out. And please, as soon as you can, start diving into your project with the Mobius strips, because that'll have a lot of cool stuff to uncover and then also to discuss with your classmates. All right. Well, thank you for joining me. That is it on this presentation. Hope you have a fabulous unit.